The magnitude of our r double prime vector, and let me obliterate the bad symbol here. The magnitude of our r double prime vector is going to be very similar in form to the magnitude of our r prime vector, except that the sine squared would be a cosine squared, and the 4 cosine squared would be a 4 sine squared, and the 1/4 wouldn't be there because the k component has become 0. So it would look a lot like this, and we don't need to write that down. It would be easy to write it down. It would not be difficult to take its derivative. It would be more or less tricky to interpret that derivative, but let's just look at the r prime of t function for a minute. When t is 0, then the cosine is 1 and the sine is 0, so that we have a 4 here. So the r prime would be 4 1/4, the square root of 4 1/4. When t gets around to pi over 2, the sine is 1 and the cosine is 0, so this is just 1 1/4. So that we see that the magnitude of the r prime vector is varying between 4 1/4 and 1 1/4. The magnitude of the r double prime vector, again, these things are going to reverse, and if you write it down and think about it, you'll see that the r double prime vector is going to be at a minimum when t equals 0 or pi, and at a maximum when t equals pi over 2 or 3 pi over 2. That is, on this picture, the r prime vector, the r double prime vector, will actually be smaller here and larger here. So we might extend this vector a little bit and extend this in a bit to show that the vector is getting larger as we move toward the x-axis. Now, we don't absolutely have to do that at this point. I'm trying to make the point, though, that this r double prime vector, this acceleration vector, has properties that we can get by simply analyzing the magnitude of the r double prime function and the direction of the r double prime function. The r prime function, as we've seen, is bigger here. So let's go ahead and graph, or just depict r prime at a few points. And we'll use this color, the r prime of t vector. It's bigger here and here, smaller here and here, but of course it's always tangent to the curve. At points in between, it'll get smaller and smaller, smallest, then bigger and bigger, biggest, and then smaller and smaller, smallest, and so forth, bigger and bigger. Whoops, kind of missed that one. Now, what we can see from this picture is that at any instant, and we've just blurred out, let's come back, come on, grab it, there we go. Now, at any instant, at any point on the ellipse, we're going to have 3 vectors. We're going to have our r of t vector, and using a different color here, we're going to have our r prime of t vector. Now this is an ellipse, so r prime of t will not in general be perpendicular to r of t. And our vector r double prime of t, which for this particular motion is back toward the origin. We see that the r double prime vector has components in the direction of the r of t vector. Again, we obtain that by projecting back here, and perpendicular to the r of t vector, and I'm going to just draw that perpendicular component along the projection line. So again, R double prime has non-zero components in the direction of R prime. Our acceleration has a component in the direction of R prime and a component in the direction perpendicular to R prime. The perpendicular component tends to accelerate us perpendicular to our motion. It doesn't change our speed, it changes our direction. The parallel component tends to accelerate us in our direction, does accelerate us in our direction of motion, changing our speed. If we take a look back at the original picture, we do see that there are 4 points at which the R double prime vector is perpendicular to the R prime vector, so that it has no component in the direction of the R prime the R prime vector. That would be this point, this point, this point, and this point. The R prime and R double prime vectors at each of these points are perpendicular. So this is something you're going to want to store away and think about a little bit, because in upcoming sections it's going to be very important. Okay, we've seen that there are cases, we've illustrated at least one case where it's profitable to express our R of t as a sum of 2 or more vector functions. And in our very first example of the beam rotating around the point that's rotating around the circle, we were superimposing the motion around the big circle with the motion of the beam. And there are many other situations where it's good to do this. Now, there are other ways of combining vector functions, okay? So let's consider another example. We've got our R prime and R double prime vectors, our velocity and acceleration vectors. We can do the dot product of those 2 vectors. Matter of fact, in finding the components of this vector in the direction of this vector, we're going to do a dot product. In other cases, we might well have 2 other functions with a completely different interpretation, not a velocity and an acceleration, but 2 vector functions. One example being I just noticed that I've continued the preceding clip with a completely different subject, but we're just going to have to deal with that. Okay, one of the cases being where you have a force and a displacement, and you take the force function and your position function, for example, and do the dot product, and you're going to get something related to the energy of the system. So there are many applications where you would be considering the function f of t, which is the dot product of 2 vector functions. Now, f of t is not a vector function because the dot product doesn't give us a vector. The dot product just gives us a number. So whatever number the dot product gives us from one value of t to the next is going to be the value of this function from one t to the next. Now the question is, how would we get the derivative of that function? Well, I'm not going to derive it for you right now, and it's fairly easy to derive. You just kind of write it out. But just to give you an overview, in this case, f prime of t, I've just kind of got myself in a corner here. Okay. Let's say that f of t equals f of t dot g of t. I'll have too many primes if I try to do this one. Okay, so we're going to say f prime of t is just going to be, okay, again, if f of t is a product of 2 vector functions, a dot product of 2 vector functions, f of t and g of t, then f prime of t is just big F prime of t dot g of t plus f of t dot g prime of t. Now that looks just like the product rule, but of course we have to make sure that the product rule really applies to the dot product, and your text does that, and you'll do that in some exercises. Again, it's not difficult though to prove that for two vector functions we do have something that's very much like the product rule, same form as the product rule for scalar functions. Another one, we got n of t equals r prime of t cross r double prime of t. For the example we just saw, r prime of t represents the velocity, r double prime the acceleration of something. The velocity is typically in a direction here, the acceleration in a direction here, so the cross product is going to be a vector in the k direction, perpendicular to the xy plane, and that's just one typical type of application where we would want to form the cross product of two vectors, call that a function, and think about what its derivative is. Now, similar to the other one, I'm going to use simpler notation. If n of t is equal to f of t cross g of t, then, well, what do you expect? If the product rule holds, a rule similar to the product rule, then we would expect that n prime of t is f prime of t cross g of t, not times g of t, but cross. You can't just multiply two vector functions. You think about that, you see why, but and then plus f of t cross g prime of t. So again, we have something very much like a product rule for the cross product of two vectors.